Can you hear me now? Online?
Yes.
Great. Sorry about that.
Sorry for interrupting.
Oh, no, no problem. Use slideshow. Where's my cursor? So I was just saying that a third of my research has been in diversity, equity, and inclusion, where we look at historical trends of who gets to participate in earth sciences in academia in the US, and thinking about ways to make our discipline more inclusive. I also wanted to start by acknowledging the elephant in the program, where I have no abstract for my talk. I wasn't the only one, but I think there are two of us. And so the reason why this didn't happen is actually because this is what's happening in my life right now. So I, on Sunday, was in Los Angeles, where I've been an assistant professor at University of Southern California for the past 4 years. And then my entire family is moving to Brown. So when people ask me, when are you moving? I am literally moving right now. This is a stopover. So since Sunday, I flew to Minneapolis with my daughter, Razia, who's 5, who's out with friends right now. My mom here and my almost 2-year-old son flew straight to Boston, and they're staying with family. And my husband, Saul, and our cat, Winter, are currently driving somewhere between Utah and Wyoming. Okay. And then somewhere back at USC is my mass spec that's also going to somehow move to Brown. So it's been a very hectic year, to be honest, planning this. And then it's all culminating right now. So when there was the email about the abstract, I was literally packing boxes that whole week, and I was like, okay, it's just not happening. So thanks for the stopover. It'll be very memorable. Yeah. But this is what I decided to do with my talk today. So I actually don't normally give this talk in this order, but because this is a meeting that's kind of surrounded by shared methodology, I'm going to talk about a very different methodology. And then we'll start talking about familiar things like magnetite and some of the rock systems that we've already heard about. So I'm going to actually start by describing the methods that I use to date magnetite, and then try to spend some time to motivate why we want to date magnetite specifically in ultramafic systems. Then I have time, hopefully, for 2 quick case studies, and I'm going to end on some challenges and opportunities. So I think this is, why I was asked to speak with you all, right? This question, like, why do we want to know the age of magnetite? And I get the impression from sitting through, a day and a half so far of talks that we all have different reasons, because magnetite is in so many different systems occurring at so many different scales that there are so many reasons why we might actually want to date magnetite. And just as I said, the way I got into this is I started my PhD at UT Austin, working with Danny Stockley. He is a structural geologist by training who does thermochronology and geochronology. And he had this idea that we would really like to date serpentinites that I'll introduce in a little bit. And he had students that had tried dating magnetite with this technique, uranium, thorium, helium, in volcanic systems. And he said, well, this is the idea, like, it's my pet idea for a long time. I think it's really high risk, high reward. Do you want to do this project, or you want to do these other projects? And for whatever reason, I chose this project. So I had my own reasons for why I wanted to know the age of magnetite that I'll explain to you in a little bit. So the methods that I'm using is uranium, thorium, helium. You might hear thermochronology, thermochronometry, or just chronometry. And some of you might be familiar with this, but usually not everyone is. It kind of depends if you have it in your institution. And so here's our age equation at the top. And I'm showing the decay chain from 238 uranium, which is the parent isotope here, to the stable daughter product 206 lead. So you might be familiar with uranium lead, a really common dating system. And so it's very similar to that, where we have these parent isotopes. We're actually using uranium, thorium, and samarium. And instead of measuring the stable daughter products of lead or neodymium, we are actually measuring the alpha particles that are produced during alpha decay that are helium atoms. okay? So that's what you're seeing, all these little helium alpha particles. And the nice thing about this is that in a mineral like magnetite, which is not known for having uranium in it, we actually have multiple parent isotopes that we can pull from. So we can measure, a little bit of uranium and a little bit of thorium and a little bit of samarium ends up being enough to get a statistically robust analysis. The other benefit is that for every one lead atom in this decay chain, you actually get 8 helium atoms. So we have a lot more daughter product that we can measure, which also helps us analytically. A byproduct of this is that the helium, though, is a small noble gas atom. So it can move around pretty easily in mineral crystal lattices. So as a result, uranium, thorium, helium age tends to have a low thermal sensitivity. One thing I realized sitting through talks also is we use a lot of the same vocabulary, but it means different things. And so you might hear that I'm going to be using my thermochronology vocabulary. So in this case, I mean that, and I'll explain it in a second, like the ages that we get are going to be dating the cooling history of rocks at geologically, kind of speaking, low temperatures. So it's a thermally sensitive technique. And so we usually use this concept of closure temperature from a geochronology perspective to help guide our minds of what this might mean. It's a simplified concept, right? But basically the idea here is that if you have your mineral forming or your rock heated above whatever this mineral's closure temperature is, your helium's able to diffusively leave your crystal such that if you went to measure our age, it would be 0, right? The helium's being produced all the time, but it's diffusing out of the crystal. It's not quantitatively retained. Once your rock cools below this mineral's closure temperature, then that helium is trapped and it's being quantitatively retained over geologic timescales. And so the age that we're going to measure is being locked in once it's cooled below the closure temperature. But closure temperature actually isn't just a temperature, right? So it's more complicated than that. It's actually a function of a few different parameters. So really common ones that we've known about for a long time is that every type of mineral has its own specific helium diffusion kinetics. So how easy the helium can exit the mineral is going to be different if you're talking about a magnetite or a zircon or an apatite or a hematite. Grain size and cooling rate that the grain size of the mineral you're dating and the cooling rate that your rock experienced also affect closure temperature. And for magnetite, we have one study that has determined the helium diffusion kinetics for magnetite that we use to then make a plot like this that we can calculate closure temperature. So what you see on the y-axis is this closure temperature. On the x-axis, I have grain diameter, which is going from very small to gigantic grains, like 4 millimeters. And we have different cooling rates that the rocks experienced. And the main takeaway here is that as you increase grain size or have faster cooling rates, your effective closure temperature goes up. And you can see for magnetite, typical closure temperatures range at around 250 degrees C plus or minus 50. Now, this paper that this diffusion kinetics come from is now a decade old. Just last year, folks are trying to get at a better understanding of the closure temperature for uranium, thorium, helium dating for magnetite. And they modeled this. So this is just theoretical. But basically, one thing they looked at is what's the impact of radiation damage or little crystal defects within the magnetite crystal, and how might that impact the closure temperature? We know this is very important for apatite and zircon, which are the most commonly applied minerals with our dating technique. And so what they found might be a little bit, abstract, kind of looking at it. But the point is that we still have closure temperature on the y-axis. On the x-axis, now we have alpha dose, which is basically a proxy for how much radiation damage has accumulated in our grains. And there are two takeaways at this point. One is that radiation damage appears to increase how retentive our minerals are. So the idea behind that is that as you create little damage zones in your mineral, they act as roadblocks for the helium as the helium's trying to find their way out of the mineral. So it makes it a little bit harder for the helium to escape, thereby raising the closure temperature by a little bit. But it also shows that, theoretically at least, the amount of damage can also change your closure temperature. And now we have a mechanism that we might have much lower closure temperatures. Maybe they're much less than 200 degrees C, down to 120 degrees C. This is ripe for study. This is definitely one of the areas we need to understand more. Okay, so those are the nuts and bolts, the important things to know about the system we're using, which namely is that your uranium, thorium, helium age that we're going to measure is either going to provide the crystallization age of the magnetite, so when that formed, or a cooling age for that host rock. And it depends on the temperature the magnetite formed. Did it form below its closure temperature and just live at that temperature forever? And it also depends on the rock's thermal history. Because even if we formed a magnetite at, say, 150 degrees C, if then we buried or heated that rock and that rock experienced higher temperatures, our age would still only reflect cooling since it last saw those peak temperatures. So this, I feel like, was an important slide to create. I haven't quite done it like this before, but what are our criteria for the magnetite we need to date with this method? They need to be big. And by big, I mean like way bigger than what you all have been calling big. So I put here as a minimum around 80 microns diameter. Really bigger than that is better. And this size is limited by how far these helium atoms travel when they're produced. So the energy to expel your alpha particle shoots them on the order of like 15 or 20 microns from wherever that host parent was. So they're being redistributed, on the order of 10s to 20 microns. So if we get so small, we're just losing it all, right? It's getting shot all out of the mineral. So we need something big enough that is like hanging on to the helium. Now, grain purity is a big one, and this is true, an assumption that we use for any mineral in uranium, thorium, helium dating. Basically, what we're saying is we have a pure magnetite crystal or zircon crystal. It doesn't have inclusions, it doesn't have big fractures or intergrowths, because that will impact our helium diffusion, which then directly impacts our interpretation of our ages, like what temperatures are they recording. We've been doing work to test, do inclusions really matter? And it's complicated. It seems like sometimes they might not matter, and sometimes they do matter. So we might get away with some inclusions in our magnetite. And then how much do we need per analysis? On the order of a milligram per analysis is necessary. And that's limited by analytical techniques. So we need enough material that we have enough counts of helium or uranium on our mass spectrometers, because we have very low concentrations in magnetite. And so as mass specs get better, and more accessible, maybe this number goes down. But this often means that we are combining multiple grains for a single analysis, or we have a big fat grain that we're breaking up and taking internal pieces. And then the timescales that we are using for this are on the millions of year timescales. And that's also true for most uranium, thorium, helium. So what's the youngest you can go? Like on the order of 1 million years. What's the oldest you can go? It's like, well, how old are rocks before they were heated above 200 degrees C, right? The oldest that people tend to measure are maybe, in the between 500 million to 700 million years old, but it's hard to actually go back into super deep time because these minerals get reset by something if they're that old. And our uncertainties on a given age are on the order of maybe 10%, which is kind of high, but it depends on what question you're asking, how important those uncertainties are. And so here's our process. So we collect a rock in the field. Then I have this one slide that is it's symbolizing all the mineral separation processes in one slide, which is actually many steps. But basically, we want to extract the magnetite intact whole grains from our rock. And so you can see here a bunch of really pretty magnetite crystals on double-sided sticky tape. Then what we do, and what I started in my PhD and we continue to do in my lab, is then we take those magnetite grains and we wanted to make sure that they're pure and not intergrown and not full of fractures. So we use microcomputed tomography, which we've already seen in a couple talks so far. So here's that reconstructed 3D CT scan of that magnetite mount. And you can see in the like brighter colors are internal heterogeneity, so inclusions or something that you cannot see in an optical microscope. But we want the whole grain, so we don't want to polish it away and look at it. We want to see it in 3D. And so then we'll filter out the grains with lots of inclusions, select them. We pack them into these little, this is like probably a millimeter big, these little, they're platinum or niobium tubes. And we put those on a noble gas mass spectrometer where we extract all the helium-4. And then we need to take the same grains and dissolve them to get all of the uranium, thorium, and samarium, typically measured on ICP-MS. So it's a lot of work. It's analytically intensive. And I just wanted to throw this in as why CT is so useful for those of us who are working with large, I'm going to put in quotes, crystals of magnetite, because you can see they're not always crystals of magnetite. But, you know, something that kind of looks opaque, behaves magnetically. By that, I mean, is attracted to a hand magnet. And then CT scanning, you know, here is a bunch of stuff intergrown with little tiny magnetite kind of clouds inside. This one behaved magnetically to a hand magnet for us. It's actually chromite with just a little bit of magnetite alteration on the surface that made it behave magnetically. So that the CT was able to distinguish that based on the density of the minerals. And then this is just a beautiful magnetite crystal, but we can see it has this big inclusion inside. So CT has been very helpful with this. Okay, so why did I specifically go to ultramafic systems or mantle peridotite systems? So before going into it, let's take a step back, right? So we all learned this in our intro level Earth sciences, that the Earth has this bimodal crust that acts as this really good separator between the surface, biosphere, hydrosphere, atmosphere, and then the deeper Earth, right? Like the core and the mantle. And that despite the fact that the mantle sits maybe 10 to 100 kilometers beneath the surface, we actually know quite a bit about it, right? Through geochemistry, through geophysics. And what I didn't realize, or maybe let's say I didn't appreciate until I went to graduate school, it's just how many places on Earth we have the mantle exposed at the surface. Because we learn about it as this layer, you know, beneath the crust. So I thought the mantle was cool. I wanted to study it, but I also wanted to work with rocks that I could touch and go see. So I was like, I guess I'm not going to do that. But actually, the mantle is exposed in so many places by two primary processes. So it can come up in volcanic systems, like you see this beautiful San Carlos mantle peridotite xenolith. The green rock in the host basalt. These tend to be small pieces, these xenoliths, and that's can be very useful for some things, but then we have tectonic processes that can deliver mantle on the order of these mountains in Oman, right? Where we can have these large slabs of mantle lithosphere thrust up onto continents. And this happens in both on land settings, subaerial settings, like we have these ophiolite complexes, like what we see in Oman, as well as in seafloor settings. And so basically we can exhume mantle rocks at any type of plate boundary, right? It can be subduction zones, it could be strike slip, it can be spreading ridges. And we know that this has been happening throughout Earth's history and, you know, happens in the modern as well. And so there's the delivery of the mantle to the surface, which is interesting within itself. But what's really cool is that when those mantle rocks are near the surface or at the surface, they completely change, right? So we have our original peridotite minerals of olivine and pyroxene, and just by adding water, right? It's like the simplest recipe. You change it to serpentine, which is a mineral, through the process of serpentinization to create the rock of serpentinite. And you have a bunch of other byproducts like hydrogen, methane, abiotically produced. You have heat, but you also have a number of other minerals that form, including magnetite. And serpentinization has implications for, I would argue, any subdiscipline within earth sciences. So, here are just a few examples. So they're really important for fluid mobile element cycling, because during serpentinization, these rocks take on up to 14 weight% water, and they suck up a lot of fluid mobile elements, and then they're able to be subducted and deliver them deep into deep mantle recycling or arc magnetism. They also, we know, are hosts to microbial communities, both in the ancient and in the modern, that are really interesting. And some people have proposed that it's systems like these hydrothermal systems through ultramafic rocks that could be the origin of life or could fuel life on other planets. We also have used them as mineral resources in human history for a long time. Everywhere from, building stones, you'll see them a lot in, as columns or building stones, these little cute Inuit carvings. But also they're hosts for big deposits like chrome or nickel that we might want to mine. And then from a more structural or rheology perspective, the process of serpentinization takes your super strong, dense, dry mantle rocks and completely changes them into something that's really wet, really less dense, and a lot weaker. So it changes fundamentally the strength of the lithosphere wherever it happens. So serpentinization is super important for a lot of things, but we have a lot of questions about both how do we get our mantle rocks exhumed to the surface, and then how long does it take for those rocks to actually get serpentinized? And it's not just serpentinization that happens. We also have carbonation. So you can see it's very common that we have carbonate weathering, either by direct replacement of the mantle or through these fracture networks. Oh, I said carbonate weathering. Let's just call it carbonation, because I want to distinguish that from weathering, which also happens to these mantle rocks. So we have these things that we can observe in nature, but we actually don't have great tools to quantify the timing and rates of when they're happening. So one question that's open is, how long does it really take to exhume these large slabs of mantle where we get these big ophiolite sequences? And then delivering the mantle is one thing, but that doesn't necessarily mean that these serpentinization and carbonation reactions are happening immediately, right? So you can deliver the mantle, but then when are the actual alteration processes occurring? And what temperatures do these processes occur over? And how might those relate to rates of the processes? And so what I put here is like this kind of holistic schematic of uplifting and exhuming mantle rocks, eroding it, creating fresh surfaces for water or CO2 to interact with the minerals. Byproducts are methane or hydrogen. And I also put this estimation that, the actual uplift tectonic processes take on the order of millions of years, whereas the erosion and weathering or microbial activity is probably much less, much faster, thousands of years or faster. And so with my work, what I've been thinking about is, to me, I think a rate limiting factor in all of this is uplift and exhumation, the tectonic process. And why do we want to know these questions? We want to know how readily these systems can contribute to these global scale geochemical, climate, or biological processes, as many people have proposed them to do, which is a really cool thought. So it really sets us up to ask some cool questions. Okay, so that's why serpentinites are important, but there's a huge problem, which many of you do know in this audience, and that's that it's really hard to get dates on serpentinized ultramafic rocks, or even to track this low temperature kind of surface exhumation of the mantle, because they don't have minerals that we use with geo or thermochronology systems that are established, or at least it's uncommon that they have them, right? Like you can get lucky sometimes, but they're not always there. So people have been able to get maximum age constraints by finding a pyroxene, let's say, in a peridotite that's exhumed, and they can use one of these radiometric dating techniques that are sensitive to higher temperatures than serpentinization happens. So they can give you a maximum age for a mantle process, but they're not telling you about alteration. We can get minimum ages if you have cross-cutting relationships, right? So you might have a mineral phase that's, you can look at the thin section and say is later, or you might have volcanic intrusion, sorry, not an igneous intrusion or volcanics that you can date, or overlying sediments, which are all super useful, and we should definitely use those, but both of these fall short of directly dating serpentinites. And so why magnetite? I already mentioned this, but one of the main reactions that of serpentinization directly forms magnetite. So you start with your olivine, you add water, and you form serpentine, brucite, and magnetite. And what these plots show on the bottom here from these two studies, effectively the same observation over many different samples. Where on the x-axis, we have density or serpentinization degree. So an unaltered peridotite has a density of about, let's say, 3.3 grams per cubic centimeter. And as you serpentinize it, the density goes down, down to 2.6 about. And what we see is that as you progress serpentinization, your magnetite amount increases. Here shown in magnetite amount as percent, here shown as magnetic susceptibility. So magnetite is a direct product of serpentinization. It is not in the peridotite or the mantle rock before serpentinization happens. And we also know that it increases with the degree of serpentinization. So let's target it. Okay, so now a tale of no tears, just trace elements and unexpected ages. Let's go into some case studies. So the case study, the first one I want to show you is a case where we're able to say when the magnetite crystallized, right? I mentioned it could be cooling ages or crystallization ages. And so this work was done with collaborators, Danny Stockley, Peter Kellerman, and Juan Carlos de Abeso, looking at magnetite growth in this really funky section of Oman that I'll show you some pictures of in a second. So Oman has the world's largest ophiolite exposure. You can see it in these blue blobs here, but in fact, we're not in that study area. We are just south of there in this inset, the Muscat Tiwi platform, which is all mapped as limestones. But in these wadis or in these canyons, you can find serpentinized ultramafic rocks. So this is what it looks like in Wadi Fins, where this work takes place. And what you can see here is some dark rocks in the foreground. These are mantle lithosphere from the abducted ophiolite, which we know this abduction occurred starting about 92 million years ago. And then in the field, you can walk and touch this late Cretaceous erosional unconformity. And above that unconformity, you have limestone deposition, shallow water limestones. That this timing, so this 66 million or late Cretaceous age, comes from fossil evidence in that shallow sequence of the limestones. And what you probably also noticed is that in the foreground, these serpentinites are riddled with these white veins. These are all carbonate veins, namely they're calcite veins, which is unusual in ultramafic systems. So part of Juan Carlos de Abeso's work in his PhD was to figure out what's the deal with these veins. And so the work they did was geochemical and petrologic modeling. And they determined that the veins in the serpentinite formed with fluids in equilibrium with this limestone depositing. That's why they're calcite, like the limestone. They have similar strontium isotope signatures. And they also did temperature. So they know that these veins were deposited maximum 60 degrees C, which will be important for us because one of the things I said you need to know is you need to know the thermal history of your rocks, right? So we know that the veins were never higher than 60 degrees Celsius, which is much lower than any closure temperature estimate for magnetite, uranium, thorium, helium. So we went there looking, I just gave you this whole thing about looking for magnetite and serpentinites. So that's what we went there looking for. And this is what we found. Okay, magnetite in the carbonate veins. There's, I won't say no magnetite in the serpentinite, but there's basically no magnetite in the serpentinite. All the iron is in the serpentine. But these are big magnetite. So there's another one. There's another one. This is the most beautiful one. This one, it was like perfectly polished. You pop it out as like perfect euhedral on the other side. So one thing you might be noticing as I flip through these is they're all different grain shapes, grain sizes, different vein textures. It's clearly a complex system, but magnetite's occurring in many locations. And why is it there? I don't know for sure, right? This is our best guess of why it's there. So we know that there's iron in the serpentinite. I said there's no magnetite, but whole rock geochemistry, we know there's like 10% iron in those rocks. And we also know from Juan Carlos's work that there's no iron being incorporated for whatever reason in these carbonates in the veins. And we also have a late stage serpentine that is not incorporating iron. So what we think is that as fluids are going through the system and picking up iron, for whatever reason, it doesn't want to go into the late stage serpentine and calcite, so it's forming magnetite in some places. And in some places, you even see what looks like a trail of magnetite from the boundary with the serpentinite going to the center of this vein and then just pooling here. So it's pretty cool. I'd be very curious if you all have found magnetite in any carbonate veins in other places, because I've given this talk at a lot of places and I've yet to have anyone tell me another instance like this. And so our interpretation is that these magnetite are related to this carbonate veining in some way, right? And we see that from those field relationships, but we also see it because when we look at, chunks of these magnetite crystals that I extracted from the veins, they do have carbonate inclusions even, or can be intergrown. And so when we do find inclusions, they're carbonate. So this is a micro X-ray CT slice. This is an SEM image, and this is what they look like under an optical microscope. So we said, okay, well, this is pretty cool. So now maybe if we can date these magnetite, we can say something about fluid flow through these fractures and the carbonate veining in these ultramafic systems. So what I did was I was able to find magnetite from 4 of those kind of vein locations and that were suitable for dating. And when I did multiple aliquots of each of these locations, so that's what these 4 points are, their average ages of many, many, many grains over multiple aliquots and the uncertainties of their average ages. And what was interesting was that across these 4 magnetite occurrences that have different textures, different grain sizes, different vein orientations, they give basically the same mean age of about 15 million years old. So that, plus knowing that these veins were never hotter than 60 degrees C, we interpret this as evidence for Miocene magnetite growth within these veins, which also has implications that this is a period of time where iron was mobile and the conditions were right to grow magnetite. So this goes back to the unexpected ages, right? So what does that even mean? We can relate this to tectonic events, which is something we commonly do. So I told you kind of this history of abduction and erosional inconformities and limestone depositions. But now we can have another data point where this magnetite growth appears to be about 15 million years ago. And this was a period when this whole system is uplifting and doming, and potentially new fractures are forming. So probably these are reactivated veins based on their textures. But I think for the sake of what I'd like to get across in this talk is what's wild about this is how would you know, right, the timing of this magnetite growth just by looking at it in the field and looking at the relationships? You wouldn't know, right? It's like by dating, being able to date alteration minerals, we're really getting into the complexity of how these systems are working over long periods of time. Okay, let me go through my next case study. So this is a case where we could both distinguish when the rocks cooled and when magnetites crystallized. So for this study, we're going to Cirrus, Greece, which is an exhumed subduction complex. Cirrus is a cyclodic island. Here's Greece, and it's right in the middle of the Cyclades. And the northern part of Cirrus, in this orange band, is where people go to study and make figures like the one on the right here. So it's interpreted as a paleo-subduction interface. So you have broken up pieces of subducting oceanic crust that went down the subduction channel and then came back up. And what's remarkable about Cirrus is that it preserves that high pressure, low temperature metamorphism without a lot of overprinting. And so this is what it looks like in the field. We're at the Compost Belt. And what you see here are blocks of dismembered pieces of metamorphosed basalts, metagabbros, metasediments that were all parts of oceanic crust and lithosphere. And then in the hillside is this matrix that is serpentinite and chlorite schist. And the chlorite schist is another fluid altered hybrid rock that's basically forming from chemical exchange between the ultramafic and the mafic rocks around it. And so this has been an extensively studied island for the metamorphic history. So we know really well that, it reaches peak pressures and temperatures 50 million years ago, and it's been exhuming through, argon and zircon, uranium, thorium, helium, and apatite, uranium, thorium, helium through the Miocene. And then there are high angle normal faults that cross-cut these exhumation structures that people have presumed happened in the Pliocene, but aren't directly dated. So we have our geologic context. We also know that through the chemical exchange and the petrology on these rocks, that they experience a lot of fluid rock interactions at temperatures between 400 and 500 degrees C. So well above our magnetite helium closure temperature. So we went here with the expectation we should be able to get a cooling age for these rocks. And so we found magnetite appropriate for dating in those hybrid matrix, the hillside rocks, these type of guys. And you can see them here. So we have this chlorite schist, which we know is like this type rock for forming during those subduction zone fluids. And they all have these really big, beautiful millimeter-sized magnetite grains, like you see here in thin section. And then we had a serpentinite within a kilometer of this chlorite schist sample. And actually, it's kind of a complicated serpentinite, right? So what you see here is a green serpentinite, and you see this white surface is talc. And these little black dots are magnetite. And we collected right below the surface in the serpentinite. But you can see in this thin section, the green is serpentine, the white is talc. And you have some of these big millimeter-sized magnetite, but you also have a sub-millimeter magnetite grain size population. So we characterize these using laser ablation ICP-MS, these grain size populations in the serpentinite. And one of the first things that we were able to observe through this, so what you're looking at here is grain size. So we have our big grains on the right of the x-axis, our smaller grains to the left, versus concentration of vanadium, titanium, magnesium, and aluminum. And each spot represents a magnetite grain and the average of multiple spots on that magnetite grain from the laser. And so what we observed is that the large grains are enriched in these elements and the small grains aren't. And these elements are important because these are specifically shown to be mobile during that hot hydrothermal fluids. So, okay, that's interesting. Then we went and we did transects across the big grains. And what we saw there, so now you're looking, each plot is a grain from the rim, one rim to the core to the next rim. The concentration is on the y-axis, and now magnesium, vanadium, and titanium are all plotted on the same plot. And what we observed is that the big grains also have these depleted rims in these elements that are about the size of our smaller grain size population. So, this could imply that we have an overgrowth of magnetite when these elements were no longer available. Okay, now we're going to get into dating them. All right, okay, so bear with me. So what we're looking at here is age on the y-axis, and then we have thorium-uranium ratio on the x-axis, and we're plotting magnetite data. Their prior work showed, we know how old white mica argon data are for this area. So that has a closure temperature of about 300 degrees Celsius, and zircon, uranium, thorium, helium for this area, which has a closure temperature of about 180 degrees Celsius. So if you recall, if we think our magnetite closure temperature should be 250-ish, we'd expect our magnetite cooling ages to plot in between the two argon and the zircon fields, right? And so the diamonds are our chlorite schist big grains, and the black circles are serpentinite big grains. And for the most part, what we see is that they do, like, they're scattered, but they do fall within this window of cooling age that we would expect for cooling through the magnetite closure temperature during exhumation. But then we dated the small grain size, and they were much younger, right? So very consistently about 3 million years old. And so this, if you recall, that what we see here are smaller grain sizes that did not have the enrichments in those elements that were active during hot subduction zone fluids, but that should still have a closure temperature well into 260 degrees C based on their grain sizes. And looking back at it, it's also probably worth noting, and remembering that this talc surface, we didn't really recognize it in the field at the time. It really does look like a slip surface, the way that the talc is aligned and it's coating the serpentinite. And I apologize, it's hard to see in this picture. So this is our interpretation of these data. So what we argue in this paper is that we actually are recording multiple episodes of magnetite growth based on grain size and texture, trace elements, and age, where we have this, and this is in the serpentinite sample with the 2 grain sizes, where we have an older, large grains growing during those hot fluids where they picked up a lot of magnesium, aluminum, vanadium, titanium, and they form these millimeter-sized crystals. And this would have happened sometime before 16 million years ago during subduction, but we're recording a cooling age through the magnetite closure temperature at 16 MA. And then we find evidence for secondary magnetite crystals that must be growing below the closure temperature at 3 million years ago. And it's right by this slip surface, which presumably could be related to this Pliocene normal faulting that others had observed but not dated. And these are small grains, and they have this depletion. And so what are the implications for this study? Well, first of all, it was cool to kind of see that you could see magnetite growth on a fault surface and potentially date timing of fluids is what I would presume related to that faulting. But it also, I think, importantly shows, again, this episodic nature of magnetite growth in these systems. And that magnetite is growing at the expense of something. So you could look at it as serpentinization or some other kind of mineralogical reaction that must be happening to form that magnetite. And so similar to Wadi Fins, I think that the timing of alteration episodes in mineral growth and all the things implied by that happening is really critical to understand actually when that happened, especially if you go to places like Cirrus here, where you go and look at those rocks and you put everything as happening in this system, right, in the deep subduction zone system. But in fact, some of it might be much more recent alteration. So just to wrap it up, we have some takeaways from what we've learned so far. We're definitely at the point, and there are more examples than what I showed here. I didn't want to, go through 5 case studies. We didn't have time for that. But basically, what I would say is we're at the phase where the more we date, the more we're learning. We can't go to a system like this and say, I know what I'm going to get when I date this rock. So far, it's often been unexpected and kind of made us rethink what our assumptions are. We are learning that texture, chemistry, and petrology are really important to couple with thermochronology. And I say that it might seem super obvious, I think, to you all, but a lot of thermochronology, when they're dealing with, zircon that crystallized in a magma, they're not paying attention to those things yet. And so this is kind of a call out to our community to be more thoughtful. If you're going to start dating iron oxides, you need to do all of this background in order to interpret your ages. And I think that, some of these results so far, I showed you maybe some of the more unexpected ones. They do really raise this question of when is the magnetite actually growing in these systems? And I will admit, I can only say this relative to the big magnetite, right? Like how much of this is sample biasing by being drawn to these big fat euhedral crystals in these systems? But I do think that what's cool about it is these are clearly really reactive systems the geologic context can be ambiguous. So the more we can date, the more we can learn. So let's end now with a few challenges and opportunities. So I made this specifically for you all, thinking about iron oxide chronometers that people have been using and working on. So we have uranium, thorium, helium on the left, the system I'm most familiar with. I talked about magnetite today, but there's a big literature of people using hematite, both to look at hydrothermal growth of hematite and hematite on fault slip surfaces. And then also goethite. Not a lot of people, I should say, not a lot of people are doing any of these things. A few people are looking at goethite to look at weathering surfaces through time. There's a literature burgeoning using cosmogenic nuclide dating on magnetite. So we have helium-3, chlorine-36, beryllium-10. And this could be used for more like surface exposure dating, erosion, glacial kind of erosion stuff. And then, as we heard today already, and many of you have come up and chatted with me about, there are a number of other cases where people have applied argon, uranium, lead, rhenium, osmium to phases like magnetite. And so all of these, are going to get you at cooling or crystallization at different time scales and temperatures. But they're tricky. There's a reason why they're not just being done run of the mill everywhere, right? And so challenges. So I would just say the challenge is that all of those that I just listed on the last slide are in a state of development still. So and I like this quote from this EOS article that was really like a call to the community about how important geochronology is. So I might be biased, but what's nice about it is it says geochronology is at the heart of all geosciences, but its ubiquity has given it an image of a useful tool rather than a foundational discipline of its own. And so what I would say is I often get that feeling from others in the community of like, just tell me what the age is. Just what's the age? And it's like, I hope what you see today is like an age is a science, like deeply a science. And we're at the cusp of kind of understanding and applying in a lot of the same ways that many of you are. And so I would say that we're still at the point where we're seeing the trees and not the forest, maybe, for these types of methods. But it's an exciting time to be identifying all these different trees in the forest. And yeah, anyway, it's going to be fruitful for a long time. And so with that, I thank you. And I'm happy to open it up to discussion. Thanks for staying awake after lunch and all that stuff. We have a question.
Hello. Who's first?
Kathy.
Thank you. My question isn't at all sophisticated. It's a sort of plea. As you might know, I've been very involved in magnetic database development. And one of the things we suffer through is trying to keep up to date with the chronology data. And I'm just wondering what you think about the state of chronology databases and the metadata that go along with them.
We're being recorded, right? Okay.
So I look at this and I think I just can't understand a lot of the time what the dates mean and why they're inconsistent. And absolutely, we can't possibly make progress on this unless we know more about what's going on.
So it's a great question, because I think that there's a lot to be desired in terms of having a database that's functional for the range of types of chronology data that everyone's producing. And our community, or one of my communities, the thermochronology community, we have a conference that reminds me so much of this, and it's happening this year as well. It happens every 2 years, and this is a common theme that comes up. So I know there are a lot of really smart and passionate people working on it, but I think that we are producing faster than we have any good repository to put it into. And the only one I know of that we can use really is Geochron. And they do have these templates for uranium, thorium, helium data. But one of the problems that we have is that, oftentimes our cooling ages, the ages aren't particularly meaningful at all. It's inverting them into a thermal history model that gives you meaningful information about your geologic system. And so how do you put that into the database, right? And I can appreciate the challenges, but I think we're at the point now where basically we're just putting in ages. Yeah, which might not be the meaningful aspect of it.
Putting in methods and.
Yeah, absolutely.
And all of the measurements so that people can go back later when they understand more about it and redo the interpretations, which is.
Exactly. No, that's
something
true.
that we've been struggling to develop within the magnetics community for quite some time now.
I think we're at a similar point where it's a struggle, right? Because you can put in the concentrations that you measured, which honestly is a science, right? Of how you convert it into a concentration, the assumptions you're making. And then the thing that we also need to do is really documenting our modeling parameters in a consistent way. And so that's been a push that a few people have been doing in our community pretty hard, but I haven't seen widespread adoption of really figuring out how to integrate it easily into what we're doing. So yeah, I absolutely agree. But we're not very good at it. Yeah.
Yeah, fantastic talk, Emily. I have a question about in the Oman case study whether you've applied other chronometers to those veins, because I'm pretty
Yeah.
I guess I'm thinking about both uranium lead on that note.
Yeah.
It seems interesting, as well as uranium lead on that Hillside,
Right.
particularly with the sort of hypothesis that they're co-genetic.
Yeah, so we don't have I'm just going to go back to a vein picture. Okay. So I haven't done uranium lead on the calcite veins. It would be interesting. I think it will be one thing. This is one of those cases, I'll admit, I'm sure you all have been there. You go to the field, you collect the stuff, you go home and you're like, damn, that's way more complicated. And then you haven't been able to go back, whether it's COVID or jobs or whatever, right? And so in hindsight, these veins are very complex. I think that works to our advantage to kind of say, yeah, there could be very easily kind of multiple phases of opening and infill and stuff like that. I think that going back and doing a really detailed uranium lead study, you'd probably find certain sections that are datable and certain sections that aren't, but I think it would be doable. How much more you would learn would be interesting. But I'm not even sure how much more you would learn.
Yeah, I guess another sort of question, which was, and I'm sure you have other constraints on the thermal history, but there was this sort of statement that was made.
Like they didn't get
the calcite formation temperatures, sort of extending that to be then that they could not get above those temperatures, right? And in this context, I'm sure you know the thickness of the sedimentary overburden and such, right?
Yeah.
Those sort of are two different.
Fair enough. So the clumped isotope temperature is on not the exact veins that these magnetites came out of, but in the same outcrop, right? My understanding is, and I asked many times, is like that will record the peak temperature it reached, that 60 degrees C, but it also fits because it's about a kilometer and a half of limestone overburden.
Yeah, in terms of clumps, you can teach it about like 100 without moving it very much, and then you start to get solid state reorganization.
Yeah.
You find that it's still the temperature's below.
Right.
And one more question was.
Wait, can I just answer? I didn't. Yeah. So we actually did do something else on these samples. We're trying to get it published right now. We did uranium isotopes, and we didn't do it on the veins. We did it on the serpentinite, the altered zones. And one of the interesting things that we found is by doing 234 uranium, delta 234. So that's sensitive to basically what it can record weathering, like type of fluid weathering, or it just gets reset to secular equilibrium because it has a short half-life. So basically, if you see an excursion from secular equilibrium, it means there has to be some sort of fluids modifying that uranium isotope composition in the last 1.5 million years. Okay. What we found looking at the serpentinites here, not the veins, is that the delta 234 is out of secular equilibrium. So how much uranium's being moved is probably not a lot, but it's enough to disturb the isotope system, which was just another like, wait, so now there's evidence for stuff happening in the last 1.5 million years. And it's like everything that we apply, we're just like getting something, you keep on finding out something new. And they seem, I mean, the other thing you could say is like, well, are they real, right? Can you trust your data? But I'm only telling you things where we trust our data. And so that is something that we've done, but we didn't expect to have that result. And we're, yeah.
Cool. Yes, my one little follow-up.
Yeah.
You hydrographically seen smaller magnetite associated with here too. And
Yeah.
Just sort of, I mean, one thing you could measure in the system too is actually, paleomagnetically looking at it and the directive, of course,
I'm sure.
Some smaller grains would be nice. Are they only these?
So it's hard to tell, but these ones, the ones that look really globular and like, those are just a lot of really small grains, as opposed to being like one big hydral grain. What's the grain size? I couldn't tell you because I see something like that and I move on, because it's probably on the order of like 10 microns or 20 microns, so it's still big, but I don't know what like subgrain in there might look like.
So do we have a question online? Related to a little bit of what Nick was just saying too. This is from Justin Funky saying, nice talk. Could the timing of different magnetite generations be reflected in the mag, or are they impossible to separate? And I mean, this is,
I would ask you, that would be great to know.
good answer. I think there's a lot of different techniques that we love to use to characterize our natural materials. We're probably thinking about certainly on your second.
Yeah.
Where you had one population of grains that had high amounts of ionic substitution.
Right.
Metals. We would see that for sure in different magnetic properties. So we would be able to take a rock like this and possibly tease out, hey, you have two different populations of magnetic compositions here. There's one, more stoichiometric magnetite and one that's ionically substituted. And there's other kinds of the reportings that maybe you could verify some of these smaller grains if they are present at all.
Right.
Maybe telling you about the timing of when they formed. Well, so it may be possible to integrate recordings with our magnetic properties in a way that's helpful to further constrain those aspects.
I do think one of the big lessons that we learned working on these types of systems is you need to convince yourself as much as you can, or gather the data you need to know if you have multiple populations or generations of magnetite before you start dating things. Because right now we're not doing this as an in situ measurement. We don't have the analytical capability on these rocks that are so low concentration to do that. So we are losing their context. We're breaking them up, extracting them, trying to take them out by grain size, or if we know they have different chemistries, characterize their chemistries before combining them into groups. But if there are other ways to kind of non-destructively hint at different generations, then that would be very helpful. Yeah.
Thank you, Emily. This is probably a very naive question because I don't know much about serpentinites. So in Bart's example of the Oman, what's the role of chromium chromite and the transformation of chromite to magnetite, and how does that affect any dating you might do?
Yes, certainly. So we see chromite in a lot of the serpentinites, and chromite is actually nice because it's one of the most resistant to serpentinization of all primary prototype minerals. So you can have all of your pyroxenes, all your olivines gone, but you still have chrome spinel. And so when I was crushing up a lot of serpentinites from different places in my PhD, I kept on extracting chrome spinel because it's opaque, it's big, they often have magnetite altered rims. And so one case study I didn't show, but that is published is at some point we tried dating the chrome spinel from a few different tectonic environments with uranium, thorium, helium, and we got somewhat promising results, right? Well, there are promising results. They're also very challenging to analyze. And so I would say for the magnetite in like the Oman system, we can see the chrome spinel in the serpentinite. That's separate from the magnetite that are forming in the veins in that system. But if you go to the Alps, you'll often see magnetite that is being formed after, like from alteration from the chrome spinel. And for the most part, I try to avoid those so far because clearly there's something more complicated going on. But I think that those are, yeah, maybe they're datable even. The chrome spinel versus like a magnesium or aluminum spinel is also something I would target because we need to dissolve them. And spinel is so hard to dissolve, but in my little bit of experience, the chrome spinel is easier. Yeah, so I think that there's a direction to go with that, but the things I showed here, we either know where the chrome spinel is, or like in this serpentinite, there's none left. Like even that was altered away.
Thank you.
Yep.
Well, thank you. That was fascinating talk. Related to, I'll follow up to the next question. I'm interested in those magnetite and the calcite veins. So perhaps I missed this, but how should I be thinking about the formation mechanism of those giant veins? How do they open? Or and also related to you seeing these magnetite, particularly precipitating in positioning in these veins. I'm not an expert. I've played with slides and SEM images of the serpentinite from California, Spain, and Alps with mineralogists. And I've seen in some cases, particularly with those, I think they're called crack seal veins in serpentinites. I see only in those veins you get sometimes chromite, sometimes magnetite in those bulbs, you don't see them. And could it be, and since I think there are a couple of images where you see chloride or 17 in these veins.
Yeah.
Could these be either calcite replacement of crack seal 17 veins, perhaps?
I think it's the first time that someone said that they see magnetite and calcite.
That I'm waiting. Has anyone else seen it? By show of hands? Great.
Wow, you're the first. I feel like
No, well, I guess I have to clarify. What I saw was in a crack seal 17 vein.
Right. Yeah, which is common. That's common. Yeah.
Calcite and chloride in those
Yeah.
different veins, but not this.
There's a scale thing, I think,
Totally.
because you can get local talc, even calcite or carbonate, and serpentine from the breakdown of, an orthopyroxene, a clinopyroxene, and an olivine in the serpentinite. These types of fractures and like veins on, these are probably centimeter scale. These you see in many places around, but also many places in Oman. And so this is clearly like physical fracturing of the rock and then fluids infiltrating and depositing the calcite. And often it can be magnesite or dolomite also that are found in these. So we see basically two types, maybe three types of carbonate in Oman. We see these types of fracture vein fill. We see active springs depositing travertine from groundwater circulation, but those you could date with like uranium series, and they're hundreds of thousands of years old. And then we see the peridotite direct replacement into carbonate that's forming these rocks called lisbonites, where you go directly from olivine to a magnesite with other mineral phases. And so they're all, we kind of use the same terminology of like carbonation, carbonate veining, whatever, but they're all clearly forming under very different conditions. And so for these types of things, it really looks like you are fracturing up that rock, whether it's from, I don't know, the uplift, extension, doming, something. There's like, they've gone through now multiple cycles of being abducted, being eroded, then going into like this quiet little shallow sea, and then being uplifted again. The kind of geologic context here looks like, okay, these veins must have formed either as the limestone was being deposited or after the limestone was already there, because the fluids are interacting with the limestone. The magnetite placement in the veins, I would say, tends to always be in the middle. Or if it's not in the middle, it's like trailing to the middle. But we almost, if you look through like this one, it's towards the middle. This is a different view. This is towards the middle, this one's in the middle, which goes to this idea of like, okay, are these just reactivated? So you have like vein forming, you fill it, then something happens that opens them up again, you fill it, and it's not until like the conditions are right in terms of iron mobility or redox or pH or whatever it is, to then want to start to grow these magnetite crystals. That's why, I had a lot of arguments with co-authors about what could be happening, and that's what has led us to kind of think, all right, if we take everything holistically, this is one way you can explain it. So I do think this magnetite, I would not say it is dating all the veining in this outcrop, but I do think that it's dating a veining episode that is growing magnetite in the carbonate for whatever reason. And I say for whatever reason, because again, I'm like, where do we find magnetite growth in carbonate? But you cannot find, like, these are big fat magnetite crystals. And that was one thing. It's like, oh, well, was that serpentinite that had a big magnetite? And then the serpentinite's gone, but your magnetite's just like hanging out. It's like, no, we're not seeing any magnetite in the serpentinite. These are growing with that carbonate. They have inclusions of carbonate, et cetera. But it must be pretty low temperature. So I don't know, like a lot of fluid. We have two more.
Thanks, fascinating talk. I want to get about the size of the magnetite.
Yeah.
You need. You just stated, maybe you showed this, I was fighting lunch, I'm sorry. But 80 microns, you said something like that, because of the length of the track of the helium nuclei and all that.
Yeah.
But is there any results about when it starts getting blocked? In magnetism, we have blocking volumes. As a grain grows, it gets to a certain volume and it has a stable magnetism. Is there a volume you need to reach in order to start keeping all the helium that's being produced by the decay? You see what I mean?
Yeah, I do see what you mean. And I don't know. It's a good, one answer would be if the magnetite's growing like above 300 degrees C, we don't care. Like we could ignore the needing to know the answer to that question, because then it could just, it's not retaining helium anyway, and it can grow. And then we're only caring about tracking when it cooled. But for magnetite that's growing hydrothermally at lower temperatures, that's absolutely a valid question. And the other thing it makes me think of, because I don't have the answer, the other thing it makes me think of is the hematite work that people have been doing. Sometimes they get these big fat petroidal hematite that they'll go and like these giant crystals. But the fault surface folks are dating surfaces that are what they would say like almost pure hematite, but are composed of, submicron platelets of hematite. And they're able to extract meaningful kind of time temperature histories or dates out of those, because the hematite, even at that size, is retentive enough of helium to hold on to helium and record time. I know that we see magnetite like that. You can see like certain magnetite that are, you can maybe get, almost a millimeter sample, but it's actually composed of these micron scale amalgamated grains. And I haven't gotten to the point of trying those because there's so many complications leading up to that point. The benefit hematite people have over magnetite people is hematite incorporates a lot of uranium. So it's uranium rich, you can get away with smaller amounts. Magnetite, we are truly battling analytical uncertainty, which is okay. Like it's a fun battle in some ways, but it does limit what we can do, how small we can go. To retain it. So I'm just saying, so I guess what I'm getting at is if magnetite is like hematite or goethite, which also tends to be very, very small crystals, it seems that even at like micron scale, they are retaining helium. They are able to. So it might not be an issue for the grain scales that we're trying to date, but that's under the assumption that they're going to be similar, which maybe they're not. Yeah, thanks for the question.
Okay, really quick. Yeah, you showed doing CT scans and like throwing out the magnetites that have inclusions. Is there any chance some of those inclusions can be, used to your advantage and be actually other datable tables?
So that's kind of what we're getting at with some of the work we're doing now. So I think it depends on what lithology you're working in, because we're working in talc schists, chlorite schists, serpentinite schists. Those are all very background low uranium phases and lithologies, such that I don't know if they're really working to our advantage here. But there's this idea that if you have this host mineral that has maybe really small zircon or apatite or something in them, then that could be contributing your helium into the host grain. And then the diffusion is controlled by the host magnetite. So you're still kind of dating something with a magnetite closure temperature, but you're seeding your magnetite with uranium and helium from like these really tiny inclusions. So people have tried garnet, uranium, thorium, helium, and shown how this can work. And I think that is something we're starting to accumulate a data set, not super intentionally. So I don't know when it'll come out, but as we go along with this type of thing. But I do think that it could be helpful. The concern we have about dating anything with inclusions is the idea that it could produce extra helium that then drives our ages too old. And so we've been trying to do these studies where we have inclusion free and then with inclusion, analyze them separately and see, are the ones with inclusions always older? And that's where, again, I kind of mentioned we are getting mixed results. Sometimes yes, sometimes no. And so then we have to figure out what that's about. Oh, what was I gonna say about inclusions? But in any case, it's something that we think about. Oh yeah, what I was gonna say. So there are a lot of ways you can make your helium age too old analytically. That is not geologically significant. One thing you may have noticed so far that was a huge puzzle and a lot of tears, just referencing that, my PhD is we kept on getting ages younger than we expected. It's hard to get young ages and like from an analytical mistake or breaking an assumption. And so that's been you can think of ways, but like also that points to something like geologically happening, that things are younger than you expect.
Any other questions? Questions online?
No, we're good right now.
So maybe I'll ask you about, you mentioned size and doing that within the list of parameters earlier, you also showed your mass and how important is it on the integrity of the crystallization of it?
So like the purity, the green purity. Yeah, we would say our assumption is that it's really important. I'm just looking for a slide that I had cut. Maybe I'll find it. But again, the main reason that we would say that we need pure grains is because we have a fundamental assumption about the way that we're about our dating system, that we understand how helium is diffusing through the grain, right? And when we do our experiments, we're doing that on, in theory, pure crystals of something. So then if we go and analyze something that's intergrown or with inclusions, on some level, we're kind of breaking our assumptions. And our bread and butter is hooking on knowing the thermal history of the sample and interpreting our ages in that context. So that would be like the main fear of not measuring something that's like really intergrown. Let's see. I would like to show you just one picture, but I had a lot of random extra slides. I may have cut it out. Here's some chrome spinel though. So this is chrome spinel. This is magnetite. This is a 2D slice, right? This is what they look like. So they all attracted to hand magnet, but then you have this very thin surface alteration and then fractures with magnetite forming in the middle. And so, I mean, it's nice to see, you can see all of this with micro CT really clearly. And we also did micro CT of the whole rock. And so this is the core sample that we analyzed. This is just like a corner of it. You see the 200 micron scale bar, and then we could make everything disappear except for highly dense minerals. And so we saw all these beautiful octahedra in the rock before we crushed it, which I thought were magnetite at this scale until I crushed it, and they were all chrome spinel with magnetite alteration rims. But this was a good way to not crush up a precious ODP core sample before you're more certain there's something usable in it, because we're not getting those back. Right. Yeah, Josh.
What are the hurdles? Sorry. What are the hurdles that you overcome in order to be able to use a smaller mass sample?
So there are two ways we could go about it. We could go to systems with higher uranium, or potentially try to take advantage of inclusions in this like kind of bottle approach. Or we could go to more sophisticated instrumentation that are able to make measurements at even higher analytical precision on lower concentrations. And I don't know, like, I'm sure you all, it really depends where you are and how much money you have, whether you can do that or not. So it's the type of thing where if you really need to know the answer, you can probably do it, but you're not going to do it on like a really large scale with a lot of samples at this point. I think I stepped into doing this. The original magnetite helium dating was a 1970 something paper by Finale and Culp at Lamont, where they went to Pennsylvania, got an ore. Okay, Rutherford actually measured helium dates on magnetite before that. But like the kind of actually dating and putting a timing and interpreting it went Rutherford 1970s and then like 2010s. That was the jump for uranium, thorium, and helium. And so there's been these big gaps. And I think that one of the issues was that we've needed the analytical instruments to kind of catch up, but then also micro CT changed the game, because there are people who are analyzing things that were completely intergrown messes and they had no idea, because they just crushed up the rock and took an opaque, shiny phase that was magnetic. And you can look at it on the SEM and see it's not, but you've polished away half your grain and you're seeing a 2D surface. So by being able to use micro CT to really just filter through all your samples at some level of resolution was something that I was able to start from the beginning, that I think really helped me be able to push forward and kind of make more meaningful sense of what I was seeing.
Okay, thank you very
Great,
much.
thank you.
Thanks for fitting us into your busy schedule.
No, I know.
Okay. But one thing we haven't done yet is